Hi, this is the Science Chef. In this video, we'll be learning about the quantum numbers and their importance in the electronic configuration of an atom. Niels Bohr, in describing the structure of an atom, proposed that electrons can exist in discrete parks of energy and are restricted to circular orbits or region with definite quantum energy. However, in the wave mechanics model of atom, which assumes the wave particle nature of electrons, electrons are not restricted to certain energy levels only. Instead, it proposes that there is a slight chance of locating an electron in a region around the nucleus of an atom. This region is called an orbital. We can therefore define an orbital as a region around the nucleus with a high probability of finding an electron in an atom. We can identify an orbital by a set of quantum numbers which can also be used to predict the location and energy of each electron in an atom. The four quantum numbers are the principal quantum number, the Azimuthal or subsidiary quantum number, the magnetic quantum number, and the spin quantum number. Let's now look at each of them in details. The principal quantum number, represented by small letter n, signifies the main energy levels or shells in the atom of an element. It has integer values ranging from 1, 2, 3, 4 to infinity. These numbers are similar to the shell notations K, L, M, N, etc. The azimuthal or subsidiary quantum number L signifies the energy sublevels present in a given energy level or subshells present in a given shell. In other words, it divides the atom into subshells or energy sublevels. Its values range from 0 to n-1 and also describe the shapes of the orbitals. When the value of n is 1, then the only value of L will be 0. And when L is 0, it represents the S subshell with a spherical shape. This means that there is only one subshell, the 1s subshell in the first shell or first energy level. Similarly, when n is 2, the possible values of L will be 0 and 1. And when L is 1, it represents the P subshell with a dumbbell shape. This explains why we have two subshells, 2s and 2p, in the second energy level. When n is 3, the possible values of L will be 0, 1, and 2. 2 being the value of L that represents the D subshell, which has a dumbbell shape. Therefore, in the third shell or energy level 3, there are 3 subshells, 3s, 3p, and 3d. So this continues with the first shell where n is 4, and the values of L are 0, 1, 2, and 3, with 4s, 4p, 4d, and 4f as the 4 subshells present in that energy level. The magnetic quantum number m sub L represents the number of orbitals present in a given subshell. In other words, it divides the subshells into orbitals and its values range from -L through 0 to +L. This implies that its values depend on the values of the azimuthal quantum number. For example, when L equals to 0, m sub L will have only one value, which is 0. That is why there is only one orbital in the S subshell. Also, when L equals to 1, the values of m sub L will be -1, 0, and +1, which explains why there are 3 orbitals in the P subshell. For L equals to 2, the values of m sub L are -2, -1, 0, +1, and +2. This is why there are 5 orbitals in the D subshell. Finally, when L equals to 3, the values of m sub L will be -3, -2, -1, 0, +1, +2, and +3, which is why there are 7 orbitals in the F subshells. The shape of the F orbitals is a bit weird and above the scope of this lesson. However, note that each orbital can accommodate a maximum of 2 electrons. Therefore, the s orbital will take 2 electrons. P orbitals a total of 6 electrons, d orbitals 10 electrons, and f orbitals can accommodate a maximum of 14 electrons. Next is the spin quantum number m sub s, which shows the orientation of electrons in an orbital. It is the only quantum number whose values do not depend on the values of the other quantum numbers, and has only 2 values, plus half and minus half. It explains that for 2 electrons to appropriately occupy an orbital, they must be placed in opposite directions to reduce the effect of the electron-electron repulsion between the 2 electrons. Now that we know what the quantum numbers are and their importance, let's learn about the 3 rules or principles that guide the order of filling electrons into orbitals. These are the Pauli exclusion principle, Hund's rule of maximum multiplicity, and Aufbau principle. Let's start with the Pauli exclusion principle. This states that no 2 electrons in an atom can have the same values for all the 4 quantum numbers. In other words, no 2 electrons can behave in the same way. This principle explains the uniqueness of an electron. For example, let's consider the electron configuration of a nitrogen atom 1s2, 2s2, 2p3, with the orbital diagram as shown on the screen. If we analyze the 2 electrons, A and B, present in the 1s orbital, you'll see that they have the same principal quantum number 1, same azimuthal quantum number 0, which is the s subshell, the same magnetic quantum number 0, which is the 1s orbital, but have different values for their spin quantum numbers, plus half and minus half. If we analyze electrons A and C in the 1s and 2s orbitals, we would observe that they have the same azimuthal quantum number 0, which is the s subshell, same spin quantum number plus half, because they are both spinned in the upward direction, but different principal quantum numbers 1 and 2 respectively. Finally, the 3 electrons EF and G in the 2p orbitals have the same values for the principal quantum number 2, azimuthal quantum number 1, the p subshell, and spin quantum number plus half, because they are all spinned in the upward direction, but different magnetic quantum numbers -1, 0, and +1 respectively. Next is the Hund's rule of maximum multiplicity, which states that in degenerate orbitals, electrons occupy each orbital singly first before pairing takes place. Degenerate orbitals are orbitals of the same energy level, and examples are the 3p orbitals, 5d orbitals, and 7f orbitals. To explain the concept of Hund's rule, let's consider the electronic configurations of boron, carbon, nitrogen, and oxygen. Boron with 5 electrons has a configuration of 1s2, 2s2, 2p1, which shows that the electron filling of the 2p orbitals starts with the boron atom. Carbon with 6 electrons has an electronic configuration of 1s2, 2s2, 2p2. Unlike the s orbitals, where pairing occurred immediately, the 6th electron of carbon goes into the second p orbital without pairing with the electron in the first p orbital in obedience to Hund's rule. Similarly, nitrogen, which has 7 electrons, has a configuration of 1s2, 2s2, 2p3. So in occupying the p orbital and in obedience to Hund's rule, the 7th electron goes into the remaining or vacant p orbital to complete the single occupancy. Remember, the p orbital can accommodate a maximum of 6 electrons, and once the filling of an orbital or a set of degenerate orbitals starts, such filling must be completed before the electrons can move to a new orbital. So, the next electron that comes will pair up with any of the 3 electrons as seen in the electron configuration and orbital diagram of oxygen with 8 electrons. Let's now look at the Aufbau principle, which says that electrons enter orbitals with lower energy level first before entering those with higher energy level. The energy level of an orbital can be determined by the sum of its principal and azimuthal quantum numbers, or n plus L value. This principle is used to describe the order of filling electrons into orbitals as shown on the screen. Electrons start from the 1s orbital with an n plus L value of 1 and then proceed to the 2s orbital which has an n plus L value of 2 before entering the 2p orbital which has an n plus L value of 3. When the n plus L value of two orbitals are the same, electrons tend to enter the orbital with a lower n value or principal quantum number first before entering the one with a higher n value, as seen in the 2p and 3s orbitals. This trend continues until it gets to 3d and 4s. Although the 4s has a higher principal quantum number than 3d, the sum of its n plus L value, which is 4, is lower than 5, the n plus L value of 3d. The same explanation suffices for the following pairs of orbitals: the 5s and 4d orbitals, 6s and 4f orbitals, and finally the 7s and 5f orbitals. The d and f orbitals are known as inner shell orbitals. So after filling the 3d orbitals, electron moves to the 4p, 5s, 4d, 5p, 6s orbitals, and so on, as displayed on the screen. Having understood what quantum numbers are and their importance in the electronic configuration of an element, we will apply that knowledge in writing the electronic configuration of the first 20 elements in our next tutorial using the SPDF notation. So if you learned anything from this video, help us hit the like and subscribe buttons, because such gestures always encourage us to do more. Don't also forget to turn on your notification bell to always stay updated with new uploads. Remember, you don't have to be great to start, but you have to start to be great. So stop procrastinating and just do it before I see you when I'll see you.